Hello, and welcome to the Lab 304 presentation on the fluid mechanics of bubbles by Emily Ballwig, Tia Enders, and Dylan Kissinger. Today we'll be going over how bubbles relate to fluid mechanics, the structure of bubbles and how bubble blowing works, how pressure can affect bubbles, why bubbles actually are able to float, how to make longer lasting bubbles, some everyday examples of bubbles, and then finally we'll wrap things up.
So I'm going to be talking about how blowing a bubble relates to fluid mechanics. When you blow a bubble, the bubble one comes in contact with the bubble solution, and that solution stretches out over the opening of the bubble wand to form a thin film layer. This bubble film has three layers in it. There is a thin layer of water in the center, surrounded by two layers of soap molecules. And the polar heads of the soap molecules are facing in towards the water, and that's what holds it all together. As you blow into the bubble wand, the air flows towards the film and stretches out and creates a bubble. So the outer surface has a surface tension that's pulling in, while the inner surface has a surface tension pushing out on it, and that's what creates a stable spherical shape. Now, bubbles are always in a spherical shape because this is the shape that takes the least amount of energy to create and has the minimum surface area. So basically, it's the most efficient shape for it to use. Bubbles have a constant balance of pressure from the air pressure outside of it, the air pressure inside of the bubble, and the pressure from the film acting inward. The air pressure inside of a bubble is always greater than the air pressure outside of it. The bigger a bubble is, the lower the air pressure is inside of it. This means that, as you can see, the two bubbles on the left side are the same size, so the pressure difference between the two is zero. When the pressure difference is zero, when the two bubbles touch, they create a straight line between them. Where the two bubbles on the right, they're different sizes, so the pressure difference between the two is not zero. And when they come in contact, they create a curved surface.
Next, we will be talking about bubble pressure. The pressure difference between the inside and outside of a bubble depends upon the surface tension and the radius of the bubble. The relationship can be obtained by visualizing the bubble as two hemispheres and noting that the internal pressure, which tends to push the hemispheres apart, is counteracted by the surface tension acting around the circumference of the circle. For a bubble with two surfaces providing tension, the pressure relationship is pressure inside minus pressure outside equals 4 times the surface tension divided by the radius. This relationship can also be seen in a graph. As you can see in this graph, as the bubble diameter increases, the air pressure inside the bubble decreases. Note that this is not a linear relationship because the graph is in log scale. One question you may be asking yourself is, how do bubbles float? To understand why bubbles float, we can look at Bernoulli's equation. We can relate 2 points below and above a bubble. We can simplify Bernoulli's equation by picking a 0 point as the point below the bubble, and then simplifying to compare the pressure below and above the bubble. As you can see, the pressure above the bubble will always be less than the pressure below the bubble, as long as the wind velocity above the bubble is greater, which results in the bubble floating. Another concern with bubbles is how to make them last longer. It is important to avoid a lot of wind when blowing bubbles because the pressure can be too intense and cause the bubbles to pop. The water quality also affects the longevity because impurities can affect surface tension. The main reasons bubbles pop is because the outside layer of water evaporates into the surrounding environment. With no water to hold the spherical structure together, the bubbles pop, which is why it helps to blow bubbles in shady, humid areas so the sun and dry air won't evaporate them. One way to enhance the longevity of bubbles is to add glycerin. Glycerin works by delaying the dehydration process. Glycerin has a unique property of being able to produce weak bonds with hydrogen. These bonds prevent the water from evaporating as quickly. Glycerin is also hygroscopic. This means that it has the ability to attract water out of the air, which may also contribute to its abilities to resist evaporation longer.
Now let's go over some everyday uses for bubbles. The most common way that most people interact with bubbles on a daily basis is in soap. Bubbles are actually a byproduct of the use of soap or detergent, which are used to clean. Water on its own is actually very ineffective at wiping away oils or any dirt or grime that may be absorbed into them, because oil is a hydrophobic material, which means it's repelled by water. Soap molecules have a hydrophobic tail with a hydrophilic head, which is attracted to the water. This allows it to dissolve in water while still interacting with oils and allowing them to be broken down and wiped away. There are countless uses for soap. At home, it can be used for washing dishes and other products. In industry, it's used to wash machined parts and the products that they make. And in healthcare, it's combined with sanitizer to make a clean, germ-free environment to prevent infection. Bubbles are also being used right now in physics research at the University of Mississippi to model and study the membrane properties of black holes. And finally, bubbles are used for entertainment. People of all ages love to blow bubbles because the combination of being round, shiny, and floating is pretty much a slam dunk for being fun. So, in conclusion, bubble membranes are formed by a layer of water surrounded by 2 layers of soap molecules. The pressure inside a bubble is always greater than the pressure outside. This pressure depends on the surface tension and the radius of the bubble, and a larger radius will mean a lower pressure inside the bubble. The floating of bubbles can be explained using Bernoulli's equation to model the situation, and we encounter bubbles countless times on a daily basis in modern life.